video, we're going to talk about the most important analytical technique to the organic chemist that cares about structure. And that is NMR, nuclear magnetic resonance spectroscopy. If magnetic resonance sounds familiar, that's because this is also how MRI machines work. That's magnetic resonance imaging. They don't like to say nuclear in a hospital if they don't have to, and so that's why it's an MRI. But the concept is the same, nuclear magnetic resonance. The nucleus is a charged particle, and as such, as it rotates, it creates a little bitty dipole, right? A little bar magnet like that. Okay, so we call that nuclear spin. So this nuclear spin, usually we can think of as kind of randomly distributed around in many different directions. But if I were to take a sample of this and apply a very big magnetic field around it, then what we would see is that most of those spins would align themselves with that supermagnet, but a lot of the spins wouldn't. And it really wouldn't even be 60 to 40. It would be more like 51% to 49% or less. But there would be a small excess of spins aligned with the field versus against the field. So this is an energy difference between these two spin states, right? So kind of like we think about orbital energies in UV-vis spectroscopy, for instance. So if I have something that's this energy, I can take one of these spin states and make it sort of flip the spin. And that's what we're going to do in NMR spectroscopy. We're going to take this set, which again has an excess of spins on the bottom state, and we're going to hit it with radio frequency energies that is going to be able to take a lot of these spins and flip them up here. So we'll end up with this kind of setup. But eventually this is going to relax back down to its equilibrium point. And when it does, we can follow that happen, right? Okay, so when one of these spins goes back down, it's going to kick out some photon of energy that's equal to this kind of difference between the two spins. So that's how NMR frequency works. I'm going to hit it with the radio pulse, and then I'm going to watch it. I'm going to watch and see how many and when some of these nuclei flip down from that higher spin state to the lower spin state. So why is this useful? So picture a plot like this. So here I've got increasing magnetic field strength, and here I've got my energy. So if I've got sort of no magnetic field, then there's really no difference between with and against the field. But the more I crank up my magnetic field, the bigger the difference is between being aligned with the field and against the field. In modern NMR spectroscopy, we have a fixed magnetic field. It's a big field, so let's say that's our magnet. Okay? And we look at one nucleus at a time. So let's say we look at a proton, we tune our probe to look at the proton nucleus at this field strength. So you might think that that's a pretty boring experiment, right? So I'll have a bunch of protons, they'll be either with the field or against the field, right? So we're kind of boxed in here. And when we run this experiment, a lot of protons will get flipped from bottom to top, and then we'll watch it relax back down top to bottom. So why do we care about this, right? So it seems like a proton should have a very well-defined spot on this, a very well-defined energy gap between these two states. And if we were just looking at a sea of protons, it would be a really boring experiment. We'd kind of get one kind of frequency spit out. But we're not just looking at a sea of protons. We're looking at a molecule with perhaps lots of different kinds of protons in different environments. Okay? And so essentially what NMR spectroscopy is doing is asking each particular proton, or whatever nucleus we're looking at, about the environment it's in and the magnetic field it feels. Okay? So for instance, if a proton by itself might be here, right, on this line. But what if I have something that is shielded from a magnetic field, right? If I've got lots of kind of electrons surrounding my proton, then I might not feel the magnetic field so much. And so according to that magnet, or according to that proton, it might be kind of more like this. A proton that is shielded would feel less of that magnetic field. And so the difference between being aligned and being against the field is less. And remember, this energy is what we're looking at. So we'll be able to tell the difference between this frequency photon spit out and this frequency photon spit out. Because again, the bigger the energy, the higher the frequency photon that gets spit out. What does an NMR spectrometer look like? So this is ours. It's in the basement of Stites Hall. Cost $450,000 back when I got the grant in 2009 from the National Science Foundation. It has a robot arm that is able to take samples out and put them in on its own. You can see the big steel Dewar flask next to it. So because we're dealing with a supermagnet here, we need to keep that supermagnet very, very cold. And so we actually have kind of a double thermos approach. So we've got this, the magnet is cooled by liquid helium. That's very, very expensive, hard to get, 4 degrees above absolute zero. It's at 4K. We fill that about once a year. And then so that we don't run out of helium that fast, we're actually cool to keep the helium relatively cold with liquid nitrogen. So that's what that big steel thing is that holds liquid nitrogen. That's actually pretty cheap, cheaper than milk. And it's held at 70K. So liquid heat, we've got 70 Kelvin liquid nitrogen, 4K liquid helium that's cooling our magnet. Not our sample though. Our sample can be kind of any temperature we want. It's usually room temperature, but we can go essentially as low or as high as we like. Our auto sampler lets us load up a bunch of runs and just kind of keep them running while we're not at the instrument. Looking at a proton spectrum usually takes something like 5 minutes a piece. If we're looking at a different nucleus like carbon, it can take up to a half an hour or several hours, depending on how close a look we want to take. But the auto sampler helps us do this pretty efficiently.